In this session, we will derive the equation for Ampere turns, which having the cross-magnetizing effect and the demagnetizing effect, and what is the remedies for this armature reaction that we'll see in this particular session. Demagnetizing and cross-magnetizing conductors. Which conductors they are contributing the demagnetizing, and which are the conductors they are contributing the cross-magnetizing conductors. First we'll see, then we'll derive the equation. That is, all the conductors which is lying between AOC and BOD, that is, I'll mark here, that is the conductors which are lying between AOC and BOD, they are contributing the armature flux in such a direction that they are opposing to the main flux. Therefore, these are the conductors which are the demagnetizing conductors, which contributing to the demagnetizing effect in the machine. Then the remaining conductors, the conductors which are lying between VOC and DOA, they are contributing the flux in such a way that they are producing the flux which is perpendicular to the main flux. Then the conductors, they are contributing the cross-magnetizing effect. They are called as cross-magnetizing conductors. Okay, that we are defining here. That is, the conductors which are lying between BOD and COA, they are producing the demagnetizing effect, and the conductors which are lying between BOC and DOA, they are contributing for the cross-magnetizing effect. Okay, therefore, if the main flux is which is acting from En to S, that is represented by the vector Fm, whereas the demagnetizing effect means it is opposing the main flux, therefore it is represented by, you can see here, these are the lines of forces produced by the armature flux between the conductors BOD and COA. There you can see the direction of the flux produced by these conductors in such a way that they are opposing to the main flux. That also I am showing in the end of this particular the slide, the main flux and the armature fluxes. Therefore, the armature flux which is producing the demagnetizing effect is represented by Ft, because it is producing the flux in the opposite to the main flux. Okay. Now you consider the case of cross-magnetizing effect. I told you the conductors which are lying between BOC and DOA, they are producing the flux which is perpendicular to the main flux. Therefore, these are called as cross-magnetizing the conductors. Now consider the remaining armature conductors lying between the AOD and COB, that is COB and AOD. These conductors carry in such a direction as to produce a flux at right angles to the main flux. This results in the distortion of the main field. Hence, these conductors are known as cross-magnetizing conductors. That is, conductors between AOD and COB are the cross-magnetizing conductors, whereas the conductors between AOC and BOD, they are the demagnetizing the conductors. Here I am considering the two-pole machine. Therefore, we have to generalize this equation for per pole. Okay, that you have to keep in mind. That is, whatever I am discussing here is the angle 2 theta here. It is made by the two-pole machine. It is a two-pole machine. Therefore, I have to generalize the demagnetizing and cross-magnetizing conductors equation for any number of poles. Therefore, I am considering here the two-pole machine. Okay. Now, here the flux produced by this armature flux between the AOD and COB, they are producing right angles to the main flux. Therefore, it is represented. You can see here it is producing the flux from right to left, whereas the main flux is from N to S. Therefore, they are producing right angles to the main flux. Therefore, it is represented as Fc, where Fd is exactly opposite to main flux, whereas Fc is the perpendicular to lines of the main flux, the lines of the main flux. Now we can observe here how exactly these are the Fd, these are the demagnetizing conductor, ampere turns. That is, you can see here, the flux, the main flux is producing from N to S, where this flux is exactly opposite to the main flux. Therefore, these are demagnetizing ampere turns. Whereas, in this case, you can see here, the flux, the main flux is from N to S, whereas the armature flux produced by the conductors between COB and AOD, they are producing in the right angle to the main flux, right angle to the main flux. Therefore, it is a cross-magnetising effect. It has got a cross-magnetising effect. Now, we will derive the equation for the demagnetizing ampere turns and the cross-magnetising ampere turns. Okay. First, I will take up the demagnetizing ampere conductors or the turns. That is, we have to remember the turns is nothing but one turn means two conductors. One turn means two conductors. If there are 100 conductors, means it is 50 turns. Means if the 50 turns are there, the number of conductors is 100, like that. Okay, one turn equal to the two conductors. That is, two conductors, if they are connected end to end, then it is called as a one turn. Therefore, two conductors constitute one turn. That you have to remember. That is the difference between conductor and a turn. That is, two conductors is equal to one turn. Now, I have got a total number of conductors in the armature. That is, the total number of conductors in the armature is Z. That is, Z is the total number of armature conductors. And I is the current in each armature conductor. That is, the current flowing in each conductor. That is, individual conductor is I am representing by I. The current in each armature conductors as the different for wave connected winding and the lap connected winding. If there is a lap connected winding, the number of parallel paths is equal to P, that is the number of poles. The number of parallel paths is equal to the number of poles. Whereas in the case of wave winding, the number of parallel paths is equal to 2. If the armature current is IA, if armature current is IA, that is a total armature current. What I mean is, total armature current is IA, then the current per conductor in the case of lap winding is IA divided by P. Whereas in the case of wave winding, if IA is the total armature current and conductor, that is the current per conductor in the case of wave winding is IA by 2. Therefore, I is equal to, that is the I means the current per conductor is equal to total armature current divided by P in the case of lap winding. Current I is equal to total armature current IA divided by 2 in the case of wave winding. Therefore, I am writing here IA by 2 for simplex wave winding, IA by P in the case of simplex lap winding. I told you that is current I is IA by 2 in the case of wave winding, it is IA by P for the lap winding. Then theta is the forward lead in the mechanical degrees. That is, because of the armature, the reaction effect, there is a shifting of magnetic neutral plate. In this case, in the two-pole machine, is a theta. Therefore, theta is forward lead in the mechanical degree. It is measured in terms of the mechanical degree. Sometimes in the questions he asks for the electrical degree, then how to convert the electrical degree into mechanical degree, that I will show at the end of this particular session. That is, in this point you can remember that Z is the total number of conductors in the generator. IA is the current per conductor in the armature. The theta is the forward lead in the because of the armature reaction, that is measured in terms of mechanical degrees. Then the total number of armature conductors in the angles AOC and BOD. We are looking for demagnetizing ampere turns or conductors, that is between BOD and AOC. That is the total angle subtended between AOC and BOD is 4 theta. Here it is a theta. Theta plus theta is 2 theta. Here is also between BOD is 2 theta. 2 theta plus 2 theta is the total angle subtended for the demagnetizing effect conductors is 4 theta. Therefore, then the Z number of conductors, that is the total number of conductors which is distributed for 360 degree. 360 Z number of conductors are distributed. For 4 theta, how many conductors, that you have to calculate. That is equal to the total number of turns. The next you have to calculate, that is the total number of turns is nothing but total number of conductors divided by 2. If you are making divided by 2 the total number of conductors, then what we are getting is total number of turns we are getting. Then we are calculating demagnetizing ampere turns per pair of pole, and you can see here the total number of armature conductors in angle AOC and BOD is, that is I told you, for 360 Z number of conductors are distributed. For 4 theta, it is 4 theta divided by 360 into Z. Therefore, total number of turns in these angles, these are the total number of conductors we are getting between AOC and BOD. Then if I want in terms of turns, then what I have to do? I have to divide by 2. Therefore, what I am getting here is, as 2 conductors constitute to 1 turn, therefore it is 2 theta divided by 360 into Z, because I am dividing this to 2 so that I am converting conductors into turns. Therefore, the total number of turns in these angles, that is angle between AOC and BOD, is 2 theta by 360 into Z. Then demagnetizing ampere turns per pair of poles, because I told you it is I am considering for 2 pole machine, therefore I am writing here specifically demagnetizing ampere turns. Ampere turns means what? To the turns, if you are multiplying the current, then it is become ampere turn. That is total number of ampere turns which contributing for demagnetizing effect is were calculated turns. To this, if you are multiplying the current, then what we are getting is ampere turns for 1 pair of poles, because I am considering 2 pole machine. Therefore, demagnetizing ampere turns per pair of poles is, to this number of turns I have to multiply the current I. So that what I am getting is 2 theta by 360 into Zi is demagnetizing ampere turns per pair of poles. Therefore, what I am interested is, what is the demagnetizing ampere turns per pole? Per pole. It is a per pair of poles. What I am interested is demagnetizing ampere turns per pole. Therefore, what I have to do is, once again I have to divide by 2, because I am considering this for 2 pole machine. Therefore, per machine it is per pole it is ampere turns demagnetizing per pole is theta divided by 360 into Zi. What I am doing here, for this I am dividing to 2, so that what I am getting is theta divided by 360 into Zi is the demagnetizing ampere turns per pole, which is opposing the main flux for each pole. For each pole, this much ATD is producing, so that it is reducing the main flux. This is one expression. That is the expression for ATD. It is very simple. Start with the theta, current per conductor, and total number of conductors between the two, that is BOD and AOC, you have to calculate. Then turns, convert conductors into turns by dividing 2. Then 2 turns, if you are multiplying the current, we are getting ampere turns. It is ampere turns for 1 pair of poles we are getting. If you are dividing once again 2 to this, we are getting per pole, that is demagnetizing ampere turns per pole. Okay, this is the expression for demagnetizing ampere conductors for turns per pole for a DC machine. Now we will go for cross-magnetising ampere conductors per turn. The simple here, the derivation is very simple. Just I will give the brief introduction that you have got a total ampere turns for a machine. In that, if you are deducting the demagnetizing ampere turns, then remainings are the cross-magnetising. The simple concept is that is total number of ampere turns per pole minus the ampere turns per pole for demagnetizing. If you are deducting, then you are getting cross-magnetising ampere turns. Okay, the same thing I am doing here. The conductors line between, that is AOD and COB or BOC, they are contributing for cross-magnetising effect. They are producing the cross-magnetising effect. Constitute what are known as distorting or cross-magnetising conductors. First I am calculating total armature conductors per pole. Total number of armature conductors per pole. How many conductors are there? Z number of conductors are there. How many number of poles are there? I am making a general P number of conductors. Therefore, first I am considering the total number of conductors per pole. Z is the total number of conductors. If P number of poles are there, therefore the number of conductors per pole assigned is Z by P. Therefore, it is Z by P. That is the total number of armature conductors per pole. It is including both cross and demagnetizing effect. Okay, all those, it is a combination of both cross and demagnetizing. These are the total number of armature conductors per pole. Total armature turns per pole. Here what I am written is total armature conductors per pole. Total armature turns per pole. Turns per pole means you have to divide by 2 to the total number of conductors. Therefore, it is Z divided by 2P here. Then, total armature ampere turns per pole, both cross-magnetising and demagnetizing. I am making here total armature ampere turns. Ampere turns means what? For turns, you have to multiply it by ampere, then it is become ampere turns. Therefore, for this Z by 2P, just what I am multiplying is I. That is becomes ampere turns. What is that ampere turns? It is total armature ampere turns. It is a total armature ampere turns is Zi divided by 2P. Then, how to find out cross-magnetising ampere turns per pole? It is a total armature ampere turns per pole. This is a total armature ampere turns per pole minus demagnetizing ampere turns per pole. Already you are derived. If you are deducting demagnetizing ampere turns per pole in the total armature ampere turns per pole, the remaining are the cross-magnetising ampere turns per pole. The same thing I am doing here. The cross-magnetising ampere turns per pole, the same I am putting, that is represented by ATC per pole. Then, what is the total armature ampere turns per pole? It is Zi by 2P, Zi by 2P. Whereas demagnetizing ampere turns per pole, that are already derived, that is theta divided by 360 into Zi. Just you have to substitute that here. Then what I am getting here is cross-magnetising ampere turns per pole ATC is equal to, that is Zi you can take common, then what is left out? It is 1 by 2P minus theta divided by 360. This is how you have to derive the equation for the cross-magnetising effect. So the sum of the remedies what we are looking for the armature reactions are, brushes must be shifted to the new position of the MNA so that we get the smooth the commutation process. Extra term should be in the field winding so that they have to compensate the armature reaction. Slots are made on the tips to increase the reluctance. Then the laminated cores of the shoes are staggered. Then in the big machines, this is the solution. What we are getting is the compensating winding at the pole sheets you have to put it. Then what is the extra number of the turns we require?